by Professor Hongwei Zhang. Professor Zhang is a professor of electrical and computer engineering at Iowa State University. His research investigates modeling, algorithmic and systems issues in wireless sensing and control networks, as well as their applications in connected and automated vehicles, AR, VR, smart agriculture, and cyber-physical human systems in general. He has led the development of open innovation infrastructures for precision agriculture, connected and automated transportation, cellular networks, and IoT networks, which have used by researchers worldwide. He currently leads the project ARA on rural broadband research. His research results and system software have served as foundational elements of the DARPA sensor network systems, A Line in the Sand and XCAL, which is the 200-node wireless mesh network and 1200-node sensor network, was the world's largest wireless mesh network and wireless sensor network deployed at the time. He's the recipient of the NSF Career Award, and he currently serves as an editor for the Transactions on Wireless Communications and the Internet of Things journal. Without further ado, Professor Zhang, if you would like to share your slides.
Sure. Thanks a lot for the introduction, George. Let me share my screen here. Okay, so can you see it now?
It's coming up now. If you can go in presentation mode, would be great.
Okay, great. All right, thank you. So here I'm going to share a few thoughts about URLLC, which has been a topic of my interest in the past, actually quite many years. So let me start with a few applications about URLLC in different sectors, just to set the context of us to think about the potential challenges and issues. So industrial control, this is where one of the prime application use case for the envisioned URLLC services. So here you can see some of the typical requirement as far as the packet loss, packet reliability, right? For example, packet loss rate is to be no more than 10 to the power of -9. And then in terms of the latency tolerance, this varies somewhere between like sub-millisecond to 10 milliseconds, depending on the type of applications that we would need to serve. And then the packets tend to be short in general, as far as control is concerned. And the communication range is actually a little bit small, within the cell or floor and so on. And the mobility tend to be low too. So that's in the industrial setting. And if you look at the outdoor, right? So connecting automated vehicles is another sector that we have been, folks have been talking about quite a bit. So compared to industrial control, there are a few key differences. One is actually the time scale, the latency tolerance tend to be a little bit higher, tend to be about a factor of 10. And then communication range, factor of 10 increase, and then speed, mobility, probably about two orders of magnitude increase over there. And then another part that, another use case, which I envision could be actually one of the early adopter of the URLLC services actually in the rural settings. For example, look at the agriculture. Think about the automated agriculture scenarios where for example, in this case, I'm alluding to the teleoperation of ground and aerial vehicles, where the latency tolerance tend to be less than 1 millisecond. And in terms of communication range, this could be actually very far, it varies quite a bit. You would have the access network, but also potentially the long distance wireless backhaul involved to operate machines in the remote farms. So I think hopefully this gives you a sense about the type of requirement and communication use cases. And then as far as URLLC as a service, as a commercial service is concerned, it's not there yet, right? So I think there has been a lot of research recently. And if we try to look at how that future may look like, we can actually look back and see what are the existing systems and solutions that may have been adopted, not necessarily in the wireless setting, but in the more traditional wired networks. So here I'm going to share two examples of the network networked URLLC systems, not wireless, but more wired networking systems that have been used in the production settings. So one example is this Profinet. Profinet is one of the leading industrial networking solutions. It has different operation mode. One of the mode of operation is called the asynchronous real-time mode, which can support the information update rate at about 1 packet every 1 millisecond, and also give you the jitter control to be about 1 microsecond up to 100 nodes in a network setting. And just like in any networks, transmission scheduling is actually one of the key key design decisions in such networks. So, and this is actually this figure showed how the transmissions are scheduled. In this simple example of like one controller and 3 devices, this kind of showed how the system works. But in a very high level, everything is actually tightly controlled through the controller in a centralized TDMA fashion. And there's actually a very well-defined pattern about which device can transmit or receive at what time, right? Those are very defined even at the design phase. And if you look at the implementation, it's actually implemented through like ASIC special purpose IC to actually just implement the TDMA, this very simple TDMA solution. It deals with issues such as cycle synchronization or time slot reservation. So this is one example in the industrial control. And then if you look at the airplane, right, there's actually a lot of discussion about UAV. And if you look at the what's used in the airplanes today, here's another example that shows a design, a very delicate design that's even more more rigorous and was stringent than what we have seen in the Profinet. There's a safe bus. Safe bus is a bus system that's used in the Boeing 777. It actually, one of the features for the safe bus, besides the TDMA pattern, which I'll briefly talk about, it actually provides a design such that it can actually provide fail-safe operation for failures of all of its components. For example, the probability of actual failure that cannot be detected is actually guaranteed to be at 1 in a billion hour of operations. Now here's the high-level diagram, architecture diagram. There's actually a lot to it, so I don't mean to take you through all the details. But each block you see here is it's like a node in the network, right? We call it line replacement module. But in the node, we have the computers, and then from the computers, you have those units that would connect the computer to the bus. And then everything actually is replicated. For example, within the node, for each computer, the interface card, the memory, and everything, cables are all replicated. And also the bus is also a fault-tolerant self-checking bus with error checking built in. And also, if you look at the schedule, the transmission schedule here, it's actually hard-coded. It's hard-coded into this table memory, and the table memory actually precisely specifies the source, destination, and the data address that's to be transmitted or received, right? So basically everything is very well defined, and also assuming that we actually know the system behavior well in advance. So that's actually what's actually working in the current wired URLLC systems, right? Now the question is, if you look at wireless systems, how it's going to look like, right? As we all know, the moment we look at wireless, many things change, right? There's actually a lot of inherent uncertainties, threats, and constraints that we have to deal with. For example, there's channel dynamics at different time scales, right? From a few to hundreds of milliseconds, depending on mobility. Also, internal, external interference, which could also vary at time scale of a few milliseconds or even sub-millisecond in the 5G type of settings. And also we have this high mobility, which would actually further challenge the design. And on top of that, on top of those inherent challenges, you may have actually those greedy or malicious behaviors that may be there. And with the softwareization of telecom, there's even more threats that's potentially there, right? And then in terms of the communication capacity and the mechanisms we can use to design mechanisms to counter these challenges, that's also constrained. In addition, there's also the need, if you look at the end-to-end URLLC systems, there's actually the need of looking beyond the wireless access network, but also look at the backhaul and also edge cloud computing applications and their co-design, right? So the question, I think the open question here is, if you compare what we have in the wireless settings and what we have seen that have been actually adopted in the industry today, where the hope may be as we, how can we actually derive such high confidence URLLC solutions and, both from wireless network and systems, are there any structure we can distill out of this chaos that can be used as a basis of design? So actually, a lot of these questions are open, and given the time constraint here, I'm going to just spend, looks like I only have time to talk about one example. So I'll take this interference control as one example because it's such a fundamental problem that's pervasive everywhere. Even even with beamforming and all those, it's still there. Of course, the severity depending on the network and traffic settings. So because signals actually propagate in an unbounded fashion in general, right? So interference itself, control itself, it is actually non-local in general. So one of the questions here would be, can we derive solutions where you could actually control interference in a predictable fashion, but using purely local adaptation control? So one observation I found is that you can actually define models that would enable this local structure, but also give you predictable control of average reliability. And this model is what you call the physical ratio K model. Let me just spend maybe 1 minute talk about what it is. Basically, the model is such that given a source and receiver, we can define an exclusion region. And the exclusion region is defined such that it actually depends on two parameters. One is a signal strength, signal power level from the source to the receiver. Another is a parameter K, which is a function of the required communication reliability from the source to the receiver. And then once this is defined, then you can actually, given any node C, you can decide whether C is actually interfere or not by comparing the interference power from C to R to the signal power divided by K, right? It's a very simple model. So one of the challenges here, obviously, is actually how to find the parameter K, because K is actually a function of many networking, uncertain networking conditions, and also a function of the required communication reliability that could be time varying itself. So it turns out there's actually also a simple approach you can use. You can actually model this problem as a distributed control problem. And in the end, you could have a solution that would require just purely local adaptation, but can give you convergence, kind of sure convergence network-wide. And so it's something that can be implemented very easily. And this framework can also be applied to essentially in all sorts of networking settings, whether it's static or mobile network, or whether it's ad hoc or cellular architectures. So with that, we could have a solution that can actually enable local correlation to enable predictable average reliability or mean reliability. So one of the open challenges will be, how do we go from the mean reliability guarantee to ensure poor packet reliability guarantee in arbitrary network settings, so that in this poor packet reliability guarantee can be a basis of enabling poor packet timeliness assurance. So you think about some of these problems, actually, the locality of the interference relation that's enabled by the PRK interference model turns out to be a mechanism that can actually facilitate a lot of the design decisions. So we have actually made some progress over there, but I guess because of time, I'm going to skip the details, and folks can check out the references later on. So with those, some of the basic, there's actually hope to design mechanisms to enable poor packet reliability and timeliness guarantee. But on top of that, there's by the time we need to integrate the wireless solutions with applications, we also need to look at the question of how do we model the algorithmic real-time capacity so that you can actually enable the co-design of wireless network solutions and systems. So I have, I have prepared some slides where I was hoping to share some note about some of the structure as far as the real-time scheduling is concerned, how you can actually ensure probabilistic poor packet real-time guarantee. But I think since the whole, I guess the session is behind schedule, I'm going to skip some of the details. Folks interested, you can look at this article, and I'll be happy to chat in more detail offline. But essentially, the takeaway here is actually through this local structure and some transformation, you can actually enable the usage of rich literature from the traditional real-time computing to solve some of the problems that's emerging in the wireless network settings. Before I conclude here, I just want to share one note that also relates to the panel after this. The question is, because URLLC is so new, right? So we need to look at where and how we can actually try out potential solutions that may become available in the coming years. So here I actually, before I share with you the era wireless testbed that folks have been alluding to, let me share one scenario which I feel could be one of the driver for the early adoption, and also especially for the early pilot. This is about the long-distance high-throughput URLLC that can be used for human-on-the-loop automated agriculture. So the setting is the following. The future of agriculture could be featured by actually automated ground aerial vehicles, which are not actually controlled by people sitting on the vehicle, but actually by farmers or even businesses running these systems remotely. And then if you look at the vehicles themselves, they more often than not, they actually carry a lot of sensors with them. And many of those sensors tend to actually generate a lot of data. For example, there's actually, even today, there's actually use of very high resolution multispectrum imaging sensor that can actually sense the plant and soil as the vehicle drive around the field, right? And those data may well need to be processed in real time at the edge and cloud. And then the decision, the result will be used to drive the actuation at the vehicles as it actually drive along the field, right? So this is one scenario that, if enabled, can actually have huge impact on agriculture. And there will be actually some pilot, actually some product that's going to be released pretty soon in the coming, actually as early as early next year. So but then there's a question: how do we, can we have a test bed that can enable the experimentation and study of relevant issues in both wireless networking and applications? And this is where the era of wireless living lab come into play. So it's one of the most recently funded the Power project. So this intends to basically look at, revisit the, look at the deployment needed to enable the exploration of advanced wireless solutions for rural broadband. So the deployment actually will be around the central Iowa, covering actually quite a lot of spatial footprint, and with many agricultural farms and rural communities involved. So a lot, the information can be found in the more detailed information about the testbed can be found on the website aeroalis.org. Right now we're still in the process of building the testbed, but some of the sites may be available as early next year. And we would always looking forward to hear from the community in terms of how this can be used in your research. If you have any questions, please feel free to reach out to me. Yeah. So with that, let me stop here and see if there's any questions. I can maybe take one or two if time permits.
Thank you. Thanks. Thank you very much, Professor Zhang. I think we don't have